general solution of a trig equation. So basically when we don't put a restriction on it between certain values. So we generalize it, and obviously there'll be an infinite number of solutions. So let's look at a sine equation. So sine theta is equal to x, and we want to find theta. Now the first thing we have to worry about is x positive or is x negative. So let's just assume x is a positive number. Now if that's true, then I know I might be in the first quadrant or I might be in the second quadrant. But if sine theta is positive, I know that inverse sine of x will give me the acute angle. So therefore in the second quadrant, this angle here must be the inverse sine of x. So that's the acute angle. It means my two solutions are either the inverse sine of x itself, the acute angle, or pi minus the inverse sine of x, pi minus that acute angle. And then obviously we could add 2 pi to each of those solutions. So we'd get 2 pi plus inverse sine of x, or 3 pi minus inverse sine of x, and then 4 pi plus the inverse sine of x, and 5 pi minus, and so on and so on and so on. Okay, but what if x is negative? The acute angle will now be the inverse sine of negative x, because the inverse sine of x will give us now a negative answer. Therefore the acute angle would be minus the inverse sine of x, or the inverse sine of negative x, depending on how you want to look at that. So alright, so the acute angle in the third quadrant will be the inverse sine of negative x, and in the fourth quadrant will also be that acute angle, meaning my two possibilities are pi plus the inverse sine of negative x, or 2 pi minus the inverse sine of negative x, which I could then rewrite as pi minus the inverse sine of x, same answer as I got over here, or 2 pi plus the inverse sine of x, which is also the same answer I got over here, because this first one could be 2 pi plus the inverse sine of x. So actually, I don't actually need to worry about whether x is positive or x is negative. I'm still going to produce the same solution. So to generalize it, I can say this. Well, theta will always end up being some multiple of pi, but I'm either going to add or subtract the inverse sine of x. And if we look at the pattern, whenever it's an odd multiple of pi, we're subtracting the inverse sine of x. And whenever it's an even multiple of pi, I'm adding the inverse sine of x. So I can sort that out by just simply putting a coefficient there of -1 to the power of k, and that'll sort out the plus minus and the plus minus. So that's the formal solution to sine. Oh, and of course k has to be an integer. Okay, let's have a look at cosine then, see what happens there. Again, let's look at if x is positive. If it's a positive, then I'm in the first quadrant. The acute angle will be the inverse cos of x, and I'm in the fourth quadrant. So my answer will be the inverse cos of x, or 2 pi minus the inverse cos of x. And again, I could add 2 pi to each of those solutions. If it's negative, so now it's the inverse cos of negative x. So I want an acute angle, and that'll be in the third quadrant or the fourth quadrant. So I get pi minus the inverse cos of negative x, or pi plus the inverse cos of negative x. But our relationship for inverse cos was that would be the same as pi minus the inverse cos of x. Playing around, and again, look, we get exactly the same answers. So once again, it doesn't matter whether x is positive or x is negative, we still get the same answers. Inverse cos of x, or 2 pi minus the inverse cos of x. To generalize this one, I can write it this way. Cos theta is equal to x, I'll have multiples of 2 pi, but then it'll be plus or minus. Because if I go back to the first solution, I could rewrite that as 2 pi plus the inverse cos of x. So I'm always getting 2 pi plus or 2 pi minus. Then I could add 2 pi to both of those, 4 pi plus, 4 pi minus, and so on and so on. That's the formal solution for cosine. Let's do tan. Same idea, let's assume it's positive. Inverse tan of x is our acute angle in the first quadrant, and also the third quadrant. I get inverse tan of x, or pi plus the inverse tan of x. Let's assume it's negative and see what happens. I'd now be in the second quadrant, but the acute angle I want would be the inverse tan of negative x. And over there in the fourth quadrant as well. So I get pi minus the inverse tan of negative x, or 2 pi minus the inverse tan of negative x. Playing around with that one, it becomes, again, we get exactly the same solutions. Because if I added 2 pi to this first one, I would get 2 pi plus inverse tan of x. Once again, doesn't matter whether x is positive or negative, we get the same answers. To generalize this one, it's just multiples of pi k, not 2 pi k, and I guess that comes down to the period of tan being pi rather than 2 pi, is why we get it like this one. So those are the three formal solutions. So if I was now to get a question like this, sine theta equals root 3 on 2, but they haven't specified what theta is in between, I can go, well, I'll just plug it into the formula. There's my answer. It's pi k plus minus 1 to the power of k, inverse sine of root 3 on 2, where k is some integer. Got to define what k is. But of course we can work out the inverse sine of root 3 on 2. There it is. That will generate every possible solution to that equation. Pi k plus minus 1 to the power of k pi on 3. That's the formal way of doing it. What you can do is this. Solve it like normal. Sine theta equals root 3 on 2. I go, I'm in the first or second quadrant. That gives me pi on 3 or 2 pi on 3 is my two possibilities. But of course, I could always add 2 pi to each of those solutions. So instead of writing it as one thing, I could write it this way. Pi on 3 plus 2 pi on k, or 2 pi on 3 plus 2 pi on k, where k is some integer. Let's do a cosine one. Cosine theta is equal to minus 1 on root 2. There's the formula. Bang. That will generate every possible solution. We can work out the inverse cos of minus 1 on root 2. It is 3 pi on 4. So I get 2 pi k plus or minus 3 pi on 4. Or doing it the other way, again, just solve it like normal. It's in the second and the third quadrant. I'd get 3 pi on 4 or 5 pi on 4, and again, okay, I'll have multiples of 2 pi, add to each of those. Do a tan one. That was pi k plus inverse tan of 1 on root 3. That one we know. It's pi on 6. So pi k plus pi on 6. This one here, I don't actually need to find two solutions to this. And that comes down to the period of tan being just pi. So I just find one solution, and that's pi on 6, and I can add on pi k, because of course the other solution we would have put down would have been the third quadrant solution, which is 7 pi on 6. But that's covered in this one anyway, because pi on 6 plus pi is 7 pi on 6. So for tan, I only need the one solution if I'm doing it that way. So now we get to interesting questions like this. Sine theta is equal to sine 5 pi on 7. Tempting just to say, oh, theta's 5 pi on 7. But of course that's just one solution. There's lots of other possibilities for theta. If I put it into my formula, I get pi k plus minus 1 to the power of k, the inverse sine of the sine of 5 pi on 7. Okay, the inverse sine of the sine, again, tempting to say they'll just cancel and I get 5 pi on 7, but no, because inverse sine won't produce 5 pi on 7. I want the acute angle, so it can only ever, remember, inverse sine can only ever produce acute or negative acute. It's got to be one of those two. In this case, it will be the positive acute, which is 2 pi on 7. That would be a general solution to that equation. Cos 2x is cos pi on 9. Plug it into my general formula. The inverse cos of the cos of pi on 9, this one's fine, they will cancel because pi on 9 is acute. So that's not going to cause me any issues. But that's 2x. Divide everything by 2. There's my answer. Pi k plus or minus pi on 18. Cos 4x is equal to cos x. So 4x is 2 pi k plus or minus the inverse cos of cos x. If x is positive, then I would get 2 pi k plus or minus x, move that to the other side, and technically because I've moved it to the other side it's minus plus instead of plus minus. Not that it really matters, it's still going to create the same two numbers. And so I'll have 3x is 2 pi k, or 5x is 2 pi k, giving me two possibilities. But remember, I don't need to go and check the negatives because it will create the same answers. But just in case you don't believe me, here you go, look. 4x would become 2 pi k plus or minus x, exactly the same. So there's my two solutions to that particular equation. 2 pi k on 3 or 2 pi k on 5, again where k is some integer. Let's try sine. Sine 4x is equal to sine x. So 4x is equal to pi k plus minus 1 to the power of k, the inverse sine of sine x. If x is positive, I will get 4x equals pi k plus minus 1 to the power of kx. But now I've got to consider something else. Is k odd or is k even? That'll produce different answers. So if k is odd, that would become pi k minus x, resulting in x is pi k on 5. I've rewritten that as 2n plus 1, because remember I've said k is an odd number. So rather than just saying where k is an integer but the integer is this, I've rewritten it as 2n plus 1 and just said, well, n is an integer because that will create an odd number. If it's even, then I would get pi k plus x, giving me this result. So again, because k is even, I've replaced it with 2n to ensure I've got an even number there. Now, if x is negative, again, it doesn't matter, because we saw before, whether it's negative or positive, we'll get the same answers. So we'll get the same as when x is positive. There's no need to check the positive and negative cases for inverse sine. Well, also for the inverse cos and the inverse tan for that matter. There are my two possibilities. Notice I changed it back to k. That's all right. This was just my working. It's still a true statement. It's just k now. I've just redefined what k is. Now, there is no exercise in our textbook on that one, so I've printed up in the handout